Hello everybody. Welcome back to In the Loop. This is a podcast by Texas Guadalupe. We are the University of Texas Hyperloop team. I am your co-host, Gavin Nader. I am the head of business and I'm a senior studying economics here at UT.
I'm your other co-host, David Spittler. I'm the head of engineering for Texas Guadalupe and currently pursuing my master's in mechanical engineering at UT.
So today on the podcast, we have Vik Parth. Vik Parth was the co-founder of Texas Guadalupe and is now the team captain of the award-winning the MIT Hyperloop team. Vik is also the director of innovation and product strategy at Aeroelectronics Research Affiliate at MIT, and his work has been featured at MIT, Wired Magazine, UT Austin, TEDx, and South by Southwest. Welcome to the show, Vik.
Good to meet you guys. Thanks, Kevin. Thanks, David. How are things with the Guadalupe team? It's been a long time since we started Guadalupe. It's been 4 years, and I've been seeing some of y'all's updates online, and it's really cool that you guys are still like maintaining like the momentum and going forward, even despite all of these pandemic related challenges. But I would love to hear from you guys. Let me know how I can help. I mean, it's really cool to kind of see that the team is still alive and still going forward. And is there anything that I could do to help? Please let me know. I really miss the group that we have in Austin. So you guys doing okay? How's the Guadalupe team doing so far?
Yeah, we're doing really good. To say that we've had a few obstacles would definitely be accurate. Pandemic can't go on campus for a lot of stuff. Mm-hmm. And then on top of that, just there was for so long a question of, is there going to be another competition? When were rules going to be announced? Stuff like that. And now obviously it looks like everything's kind of moving over to the boring competition. Mm-hmm. So yeah, it was weird trying to find like, all right, then what's our identity as a team now? If we're not, just going after this competition, then what are we going after exactly? We were really lucky with the Icon partnership last semester, and then being able to kind of work up for a design review with that. That was really beneficial for us. And now we have some access back to on-campus stuff. The goal is to build a prototype this semester, work on manufacturing processes, stuff like that, and kind of like a more low risk scenario, and then hopefully go on from there. But again, it's still weird because do you build a full pod for 150-foot track? What do you kind of do with that? So There's still some questions long term. But I think we've kind of figured where we want to go short term.
Mm-hmm. And your team, how big is your team right now? Even during this pandemic, do you guys have people that are still willing and able to work on stuff?
Yeah, I'd say we're at 2025 active right now.
Oh, wow. Okay.
Mm-hmm. And we did pretty decent recruiting for everything virtual. I think we have 9 to 10 people interested. We're going to do some more interviews over this next week. But surprisingly good for like, hey, do you want to be on Zoom even longer? And people are like, sure. Yeah, totally.
and also, so people, oh, sorry, go for it. Yeah.
Yeah, I was just going to say it's been tough too because competition was a big recruiting aspect. Mm-hmm. And now that there's no clear competition, it's been way more tough to recruit. So.
Mm-hmm. Well, I think it's very, you guys have done an amazing job in continuing the legacy of the team and everything. And I think, as you guys keep working on some new ideas, new concepts, I think you guys are the ones that are changing the landscape of what can be done. And so I think I would encourage you guys to not give up. I think that's the biggest thing is, there's always going to be people interested in this kind of work. And, you want to keep that fire going, right? And I think that's what we started with. When we started meeting in that classroom, it was like ETC, from some classroom in the first floor. We just had like meetings, seven of us. It was just like 4 years ago. James, myself, Patrick, Deb. We would just meet weekly, and just start, designing stuff on a chalkboard. And then, a year later, we're building this pod for Elon Musk, right? And it's just like, we never really expected us to do that. And I think the fact that you guys have come a long way since then shows that there's a lot of value to what you guys are doing. And so I would love to see you guys keep flourishing. And, if there's anything that I could do to help you guys out with that. And I know Hyperloop right now has been a little weird with the situation given the pandemic, and there's not really a Hyperloop competition happening this summer. However, I do think that what we learned over the past several years on the pod development can still be used for like future systems that we're building like underground, right? So I mean, the boring competition is really in a way like a stepping stone for Hyperloop, because in my opinion, I don't think a Hyperloop can be built above ground significantly cheaper or than like typical systems. And so, I think it makes sense that Elon is going underground. And I think the purpose is to eventually have some kind of a high speed, low, like partially evacuated system. I just don't know, how long that might be or like how fast that might be. But all the stuff that we're learning through the Hyperloop program will still be relevant to this. And I think, I think what you guys are doing, you guys have a great space, a great track. Maybe we can think about ways to, improve upon that as well. And yeah, I mean, I'm more than happy to help. And our team here in Boston, as you guys know from last year, we were part of the Hyperloop 3 program. And this year we've been focusing mainly on the boring program. And so we've had, we recently actually just got admitted to the boring competition. So if you guys look up on the boring company website, we're actually going to be competing with like 11 other teams this summer. So I'm just advising that team right now, but it is a tough problem. I mean, digging a tunnel for 30 meters in length and about 6 feet in diameter, it's not a very easy task. It's a very different problem than like, just building a pod that goes really fast, but we'll see what these challenges look like.
For sure. Yep.
Yeah, I'm definitely kind of interested in what led y'all to make the decision to switch over to being a tunneling team, and just like how different of an engineering problem that is, and like all those kind of just technical skill sets you need to pivot to be able to really be successful in that.
Yeah, I would say in our perspective, it was like, we knew the infrastructure to build like sort of like, an autonomous system, right? Something that works like with high power, high energy, and being able to move fast. In this scenario, we're kind of the main thing is that it's rotational, right? Everything's more like looking at rotational energy and like looking at how do you dig tunnels, and it's like fundamentally a different problem entirely. And I think it's more dangerous, to be honest, because you're dealing with a lot of sediment and rock and soil as well. So ultimately, the composition of the team has to change a little bit to be more civil engineering focused and civil and structural engineering focused, to be honest.
Maybe even like geology to an extent, probably.
Yeah, you need a lot of geology. To be honest, geology students, geology experts who are familiar with this is really important too. So that's really a big shift for sure. At the same time, it's like, we don't want to like, completely shift over to digging tunnels and not think about Hyperloop. It's like, we're still thinking about Hyperloop. We're thinking about ways that we can still build upon the existing design that we had. Maybe doing some hybrid systems, leveraging maybe both a combination of magnets plus air levitation, or looking at better ways to do propulsion, or looking at better ways to do stability, right? So I think those systems are still important. But at the same time, in order for us to have a deadline, usually teams work better when they have a deadline, right? So since there's no deadline in place for Hyperloop, it's hard to get a team together to build something and there's nothing physically to build for or to, right? So we're using the boring competition as a way to kind of generate a lot of interest, a lot of, people that are able to kind of just commit to a deadline and just start working on that. And I think, we don't even know the actual date of the boring program competition. They said sometime in the summer, but it is open to anyone who's interested and able. So if you guys really are interested in working on the boring program too, we can definitely find ways to kind of collaborate again. And I think, to be honest, this program is very more open-ended than the Hyperloop program, just because of the nature of the problem. And, we have to, not only dig a tunnel, but we have to figure out how are we going to, put material in the tunnel to keep it stable. How do you, ultimately build a track in the tunnel to have things drive through, and also be able to navigate through the system and figure out how accurate your tunnel digging system is. And so if you look up like tunnel boring machines, right, they're very big machines that are used for digging very large, like 30 feet, 50 feet, 100 feet diameter tunnels. We're not looking into those typical machines for this kind of a project. We don't think that's like necessary, to be honest, to build a tunnel that's like maybe 6 feet in diameter. You can use several other methods called pipe ramming, or like there are things called auger boring machines, AUGER. So these machines are actually commonly used to build like oil pipelines and stuff. So we're actually looking at alternative methods to dig tunnels. And I think for the perspective of this competition and this program and the timeline that we have, it makes sense that we try a much more scalable in terms of like what's actually doable for this program, right? I mean, we're not trying to build like a 10-mile track, for people to transport underground, right? That's not what we're doing. We're just trying to build a tunnel as fast as possible. And to be honest, tunnel boring machine is not really the fastest solution. It's great for a big solution, but not really a fast solution, if that makes sense.
Yeah, sure. Yeah. So would you say most of your team has, like, have you been recruiting more, do you know, for tunneling? Or like, are you kind of splitting?
Yeah, I think so. In Boston, things are still all remote as well. I think we have been getting some interest from civil engineering, structural engineering departments, but I think it's still not easy, just because people don't want to be in Zoom all the time to meet, or they want to be able to build stuff, right?
Yeah.
And we don't have the ability to go in machine shops necessarily, or go in the shops to build anything at the moment. So what we're doing right now, the team is kind of brainstorming, okay, well, can we do some really robust design, like simulations and design in the meantime, and to maybe work on the navigation system potentially, or even the structure stability system of how are we going to dig the tunnel in the first place. But we have been looking into several companies that also build tunnels. So let's say, I think there's a few out there in the US that actually build auger boring machines already. So we're trying to see if we can actually work with existing machines that are already built, and be able to retrofit them for our purpose, right? So I honestly think that building a tunnel digging machine from scratch in less than 6 months is very unreasonable, unless you have a significant amount of capital and resources to do that, right? I mean, these machines can be like a couple $100,000 to $1 million just to obtain, right? And I don't expect anyone to be building a machine from scratch, let alone building a massive battery pack that's going to power that machine, right? And these machines typically are gas powered anyway. So again, we're trying to figure out what problem can we crack first. And I think the biggest problem is, I don't really care about power right now. I care more about the digging machine ability itself. Like, how fast can you dig, and how is it digging, like the drilling bit kind of structured, right? If you look at the tunnel boring machines, they have a very large sort of a diameter, and they have like many different pockets within the tunnel boring machines, and they have individual bits that are running. And some of them are diamond coated bits too, right? But it's a very expensive, right? And sometimes a pipe ramming technique could be a lot more efficient for the size of the tunnel we're building. So a pipe ramming machine basically just stuffs the pipe inside the soil, right? If the soil is sort of not as dense or not full of rock, you can just stuff a pipe in there and suck the soil out, and that's like a quick way of making a tunnel. And you don't really have to use like a tunnel boring machine to do that. And so again, the competition is more about speed. Again, this is sort of another thing that it's a bit frustrating, is that if you guys notice in Hyperloop, a lot of companies, right, it's all about speed, and companies were, they just built small little electric dragsters, which weren't even Hyperloop pods, and they're trying to beat the speed limit of that specific design that they were working with, but it's not really a scalable design, right? And so I think it's going to be similar again this year, where people are going to be building machines that aren't actually fully scalable for full Hyperloop transport systems, but they're just trying to build fast tunnel diggers, right? And I think, in my opinion right now, given that we don't have like tremendous amount of resource or people to build a full-blown like a tunnel digging machine, I think what we could do is to build at least something that could be smarter than what's already out there, or at least retrofit what's already out there and make that better. And so that's the approach that we're taking right now.
Mm-hmm. So how do you fix it just being a speed competition problem? Is that just like we need more overall criteria as like a competition? Because this was a thing that we talked a lot about with Hyperloops, like, oh, it's just always what number can you reach? Highest number wins.
Yeah, that's always like it's to me it's a bit annoying to have to work with that value, but I think the public always wants like a fast moving pod, right? And I think for this scenario specifically, for the boring program though, we can't really say what is the best approach here, because I think safety is going to be number one for sure. I mean, I'm honestly, to be honest, most concerned about the safety of the entire system. Like, we're bringing a machine to some desert in Nevada, or I don't know where it is. And like, we have to make sure everything's loaded properly. I don't know how much it's going to be viewable to the public, but essentially, we're doing a construction related project that requires a lot of oversight and personnel, safety related personnel. And so I honestly, I'm not sure at the moment of what their metrics are to judge in terms of the speed or of the tunnel program, but I do know that ultimately they want to be able to build a 30-meter long tunnel as fast as possible, and that could use any technique. And honestly, I don't expect anyone to bring a tunnel boring machine to the competition. I mean, that's just if they do, I mean, that's impressive. That's a massive machine, but um, they're companies, and there are a lot of other individuals especially in the US and the UK, who are actually already good at building tunnel boring machines. And I don't expect any student team to be building this on their own. And let alone like, flying this machine from like the UK to the desert. It is sort of
That'd be
like,
insane.
I don't
Yeah.
know what that's going to look like, right? And so honestly, I don't have too much information at this moment to kind of understand what the scope of the competition is going to be like. But our main approach right now is making sure that, can we build something that's small, quick, and easy, somewhat scalable, and at least can dig a tunnel in a decent speed, right? And I don't really care about trying to win this competition at this moment. I just care about, let's just build something that actually works, right? And I think that that's actually going to be the hardest part, to be honest.
Yeah, we definitely feel the same way about having like a deadline and
Mhm.
having something for people to build. Um, the thing that we were kind of concerned about was not just being like an Elon Musk yes man, and we kind of wanted to try to figure out how to be independent from like the SpaceX competition and whatever problem he throws at us. So we're just trying to figure out how we stick to Hyperloop and how we just stay independent and keep pursuing Hyperloop. And I'm sure you all felt the same way, but it is definitely
Yeah.
not like a project.
What are some problems that you guys are really interested in, specifically around Hyperloop at the moment, given like what your team has, and what you guys have in terms of your skill sets? What do you guys think is like a reasonable problem to tackle?
So
I'd
I
say one of
know,
the bigger ones. Oh yeah, go ahead, Gavin.
yeah, well, we were interested in figuring out how to test air bearings at high speed.
Mhm.
So last semester we had this project called the Wheel of Death, which was basically just a really fast spinning plate where you put the air bearing on just to see how it reacts. So that's one thing that I was pretty interested in. And then, yeah, just being more efficient and figuring out how air bearings can apply at full scale for sure.
Mhm. I still think there's a lot of value to air bearings. I think they haven't been really tested to the point where we know for sure that it is not going to work. I think there's a lot of unknown variables still in the air bearings, and that's what we're trying to do. Actually, in a year and a half ago, is we actually built a similar like wheel of death in Cambridge, and you guys I think saw that, I think, right?
Yeah.
And we spun it at what was it, like I think we got to about 100 or 80 miles an hour with that wheel of death, and there weren't any issues at all with the air bearing. Everything was functioning really well, and even worked okay even with the gaps that were in the plate that we were using. We kind of simulated some small little gaps in the plate to almost look like in the full track you're not going to have a fully smooth surface. And even with that, the air bearings functioned really well, and it just kind of smoothed over, right? And I think we were more concerned about like the airflow, like how much airflow we're losing, because it's a combination of both the airflow and the pressure, right? How much cubic feet per minute and how much psi is in the air bearing, right? And we noticed in the competition, roughly we were operating at 15 to 30 psi for each bearing, and then I have to check. It was like our flow rate was like 200 SLPM. I don't know how much that is in CFM, but I have to do that conversion. But it was a significant amount of flow for each bearing. So like 200 times 4, 800 SLPM per pod, right? So I have to do that calculation for how much that is in CFM. But there's significant amount of flow that's going through these pods, and how do you optimize that flow rate so that you're still maintaining enough lift but also not wasting too much air, right? And I think given the 2 small air tanks we were using at the moment to do the testing, we're able, if the pod is going at 200 plus miles an hour, you can easily hit several miles in distance, right? Even more, given like the amount of air we're hosting on the pod, right? So, ultimately for a scalable solution, you would have to have some kind of a, some kind of onboard compressor or something to kind of feed in air to the air bearings. And to be honest, you're not going to be operating at your vacuum anyway. It's too expensive to operate a tunnel in your vacuum. You will always have air, and there will be some air drag regardless in your pod. And so that's one question I still have for a lot of these magnetic levitation companies, is that you're still putting a pod through a tunnel, and there's still going to be the I don't know if you guys heard of the Kantrowitz effect, right? There's still going to be this effect where the air builds up in the tunnel, and you have to suck it out anyway, because you're not at a full vacuum. And so either they reduce the diameter of the pod such that it's minimal compared to the diameter of the tube, or they just have to find a way to suck the air out, and make sure it's being, it's almost like you push a syringe, right? If you push a syringe, you can't, if you push it fast, like the air buildup at the very end, it prevents you from, getting all the way to the very end. So same thing happens in the Hyperloop too. So I'm curious to see how companies are kind of battling that situation.
Yeah, I think that's why in Elon Musk's white paper he had the fan at the front, and he was using that effect, I guess, to fill his air bearings in his tanks.
Yeah.
How do you think that issue would be resolved, especially in like a tunnel-based system where you can't exactly have places to take out air along a tube? What do you do at that point?
That's a good question. Like if when we saw the boring tunnel a year and a half ago at SpaceX, right? They actually had a little ventilation shaft above the tunnel. So you had the full tunnel, and then there's like a small ventilation shaft on top of the tunnel. And that's probably the purpose, is to kind of suck out any air or anything sort of in the system. I think one of the things they're trying to do right now is trying to, by using electric vehicles, you don't have to worry about gas emissions in the tunnel, which is a big problem too, right? I mean, if you look at I think England built a tunnel underneath the ocean to go to France. You have to look up the England to France tunnel, and they had to build a lot of these different ventilation shafts in that tunnel because air buildup, because you have all these gas emitting vehicles in there. And there was actually a fire that happened in one of their tunnels, and there's a huge public event because people were stuck in the tunnel and there's a fire happening. They have to evacuate them, and so these are all safety issues that are part of like digging a underground tunnel. And let alone if you want to build a near vacuum type of Hyperloop underground, I don't know the amount of stress that's going to be, because you're basically building a pocket of empty air underground with all the pressure above the surface, right? So in terms of like buckling, in terms of structural stability, there's a lot of things that can go on in that scenario, and we don't really have enough data to show that if that would even work. So no one's really built a vacuum underground, really. So or like a Hyperloop type of system underground yet. So I don't really know what that process is going to look like, but I do know that building a tunnel needs some kind of a ventilation regardless. If you're trying to make sure that everything is safe for travel.
So would your tunneling machine be electric? I'm guessing not, right?
So right now, most machines are not electric. They're all, diesel based or gas based. And so given that, we're just trying to retrofit an existing machine to help dig a tunnel maybe faster. But ultimately, I think they can be electric based. I think the Boring Company at SpaceX is retrofitting one of their TBMs with the Tesla drivetrain or something, and they're trying to see if that could power up the tunnel machine. Again, safety wise, I think it's less. It doesn't have as much emissions, but I'm not sure how efficient that is, because it does take a lot of instantaneous power to do that. And in terms of how fast you want to dig and how long you want to dig, it does take a lot of energy to do that.
In terms of the future of the Hyperloop competition, there's always this talk of like, oh, the next competition is going to be a tunnel and it's going to have a curve and it's going to be, 5 kilometers or whatever. Do you think there's a possibility that now, all right, so we're doing all this tunneling stuff, somehow this leads into a new track for a Hyperloop competition?
I actually do believe that. Actually, I mean, we don't know when that's going to happen. Like Elon did say that last year, it's like next competition is going to be like a 10-kilometer vacuum tunnel, right, underground. And I mean, if he's keeping to his word, I think at some point there will be some kind of a track that will be created. I think part of this current boring competition is to maybe start creating the foundation of that track. And I don't know how long this track will be, if that will be built, that 10 kilometers will be built this year or next year. But I do believe that there is a possibility of that being a future competition landscape, because that was one of the biggest complaints we've had at the Hyperloop competition, is that the track wasn't long enough. Because if you really want to hit 600 miles an hour, that means that you have to basically accelerate at a decent amount to even hit that speed within the first 1,000 meters of your track before you decelerate, right? And given a track that's not even 1 kilometer long, you can't really do much in hitting that high of a speed, right? I mean, you would just accelerate really fast and just brake really fast, right? And so with a longer track, you have a longer slope to kind of accelerate with and be able to hit a higher top speed.
Mm-hmm.
Yeah,
I think it's kind of interesting too, because one of the big kind of advantages of Hyperloop is, you'll have all this coasting ability, all this passive, really high speed movement, and then you never get to demonstrate any of it. You never actually get to see the part that makes it so special.
Yeah, I know, you're right. And I think I do like some of the things that the European teams are doing right now. Like if you look at, I think there's a company in the Netherlands. They came out of the Delft Hyperloop team, and they're building their own Hyperloop track, their own system, and they're using a transport system that is going to be having magnets on the top of the tube. So it's almost like a roller coaster that carries you through the tube, instead of having a track on the bottom surface. So it's like a elevated pod. It's going to be almost like a gondola, like that would just kind of drive you through the pod or through the tube, using some form of electromagnetics in the track itself. And I think they're adopting that approach mainly for track switching. Like when you're imagining trying to switch tracks within the tube, you're trying to go from one track to the other track. Being able to switch that lane is extremely important at those high speeds. And so they maybe have determined that building a track like what we have at SpaceX, like with the track on the surface, on the bottom surface, is not maybe the ideal approach. And so I think Virgin Hyperloop also is adopting that approach. If you looked at their latest track design, their actual system is the electronics, and the track itself is actually on the top of the tunnel, not the bottom.
Mm-hmm. That's interesting. We actually had Josh Geigel on, co-founder of Virgin Hyperloop, a couple of weeks ago.
Cool.
And we brought that up, and that seems like where the commercial route is going. And it seems like track switching is going to be extremely important for kind of having that viability of multi routes off the same tube, essentially.
Yeah, no, I completely agree. Yeah.
So do you think that's something that would then ultimately be a goal incorporated into a future Hyperloop competition then, of having that top base levitation? Or is that something that would just always be almost to an extent an advantage in the overall Hyperloop scheme, but almost shooting yourself in the foot in terms of being able to hit X number or something like that?
I think the whole track switching, the sort of like the having the suspension all the way above and the top of the track, it adds a lot of complexity to the system, especially for like a Hyperloop competition. And I think I honestly think the only value of that is if you have a long enough track to work with. And I think if the track is only 1 kilometer long, I don't think there's going to be a need or like a interest to kind of build a whole complex kind of a suspension structure for the pods. But if, let's say you have a 10-kilometer track, right? And maybe that track is maybe split into different lanes, there is a potential for kind of building that in there too. Again, I don't think SpaceX is going to be doing that necessarily. I think they're not really trying to build full Hyperloop tracks right now. They just want to build simple lanes underground that let cars move. And for them, I think they're trying to make a decision based on more efficiency and more based on cost at the moment, right? If they're trying to build a track for under 10 million a mile, or that's, you can't really have too many complexities involved in that. And I'm assuming these other tracks that are being built by Virgin Hyperloop or even the European companies can cost anywhere for 80 to 100 million a mile. I mean, they're very expensive. I mean, imagine putting a magnetic levitation system, a suspension system, a sort of a gondola type movement and track switching all in a partial vacuum. Like, I don't think it's going to be very cheap,
Mm-hmm.
So
what are your... Oh, go ahead, yeah.
Makes me wonder what you think like the theoretical limits are for a student competition. Because theoretically we're supposed to be testing full-scale feasibility, right? But as we've been discussing, that's kind of hard for student teams to do. So I'm wondering, in your eyes, what do you think is like the role of the student competition?
I think it should be always about innovation. And I think speed is great. I mean, it's cool to build something fast, but ultimately, if you're doing something that's already been done before, I think it's a waste of time. And unless you think there's a significant improvement to what you're doing on top of other things, right? So, people know maglev works, right? It's already proven it's going to work. I guarantee it even works at 600 miles an hour. There's not going to be an issue with maglev, but we know it's already a working technology, right? It's something really you could do on top of maglev to make it even better. I mean, there's a lot of research and development going into maglev and passive maglev, active maglev, superconducting maglev, right? There's so many different options already. And I think, from a student team perspective, right, there's a lot of research material already out there on maglev. And I would, if you want to take that approach, I would try to focus on problems of making maybe much more efficient magnetic arrays. Maybe that could be another option. But in general, though, I would pick areas that are more unknown, right? So like maybe looking at hybrid concepts, looking at new propulsion methods, like maybe even looking at gas thrusters, or even like how do you make electric propulsion even more powerful, like using linear induction motors combined with air levitation, right? So things like that are innovative concepts that are different that people have not tried before. And I also, think about it from like just in terms of like transporting goods, right? So you don't really need to have a vacuum. Vacuum is just more like a cool thing to have, but it lets you go faster, right? But building a vacuum track is very expensive. So why not use like simple partial or even like non-vacuum tracks to build systems that can carry a lot of weight, right? I mean, a lot of times air levitations, the purpose of that is to support lots of weight. You can move entire airplane hangars on air bearings, right? And yes, they may be like very slow, but like if there's a constraint where you have a linear track that's only going in one direction and only have a limited amount of space to work with, you can consider that as even like a freight transport kind of a opportunity, right? I mean, thinking about how much freight we're moving in the industry now, there's always going to be a need to move freight more efficiently. And I think of that as a very innovative approach to maybe transportation. So those are my thoughts, right? I think just looking at problems from like more from an innovative perspective and trying to do something that people haven't really tried before.
So one more for me, from like SpaceX's perspective, what do you think is their main motivation for hosting this competition? Do you think it's mainly for this technology innovation, or do you think it's a lot about recruitment?
I think it's a mix of both. I would say more for recruitment and more for public excitement. I think they want to generate a lot of excitement around this, and I think it's cool that people have get to work with such cool vacuum systems and new like technologies that are at SpaceX. And I think it's a great way to kind of get the public like really interested in what's going on. And I think that's what happened with Hyperloop when it first started. But then as you noticed, it dwindled down because, over the years, it's like, there's only so much you could do in that certain track, right? And I think if you don't focus on innovation, it doesn't really become very fun anymore. It's just more like, let's just build another fast electric car. And, it's not really, I don't know, to me, it's not really new and exciting. So I think if they really want to continue that excitement, we really need to think about it from a innovative standpoint and not just like, oh, let's just build a fast car.
So how do you think that the Hyperloop competition is different from a student competition like Formula SAE or something, where realistically for the last decades and decades, they've been building very similar cars in terms of what they can do, what they look like. You see a row of these cars and they're almost all essentially the same.
Yeah.
That said,
like,
you still have these students coming in every year and wanting to do this competition. So how does the two kind of differ?
Oh, okay. So that's a good question. So you're saying that the cars that are being built for Hyperloop are very similar to Formula SAE cars?
I'm saying that, for instance, like you're saying the staying power of Hyperloop was kind of dwindling because, oh, this has been done before, same track. There's not a lot changing within the competition. That said, you have other competitions where realistically they haven't changed for a long time now, but there's still the same amount of hype. There's still students really interested in it. What's kind of like the difference there?
Well, I think the fundamental the problem set's different, right? I mean, Formula SAE, it's like there's a lot of more strict rules in terms of winning that competition. Or there's a lot of additional things that are required in building that electric car, or that even right now there's Formula driverless, right? There's also the Formula team that's also doing like driverless vehicles too, and that's been a big popular thing that people have been working on. But I think the thing about Hyperloop is that it is a problem that is fundamentally different from anything else. So you're basically creating a whole new transport system. And I think if that's the vision, then that's obviously, to my opinion, I think still more exciting to me than like, building another electric car, right? I think what's happening is that people are trying to just bring in the sort of, to make things go faster. They want to just adopt methods that are being used already in industry, kind of to make fast electric cars, and then putting that in a Hyperloop setting, right? But this is for a student competition. I think that's not really scalable. And so I think if we're trying to really get as much value from this Hyperloop program, I think it's cool that we have access to a really cool vacuum track at SpaceX. We have the ability to kind of do testing in like the world's only 1 kilometer vacuum system. I think that's something that you don't really get to have on a day-to-day basis. And I think that infrastructure that's there is something that the Formula team doesn't really have, right? So I think being able to do that, test on that, we may not have as many rules or as many constraints as the Formula teams, but I would say the excitement of that, working in a problem that sort of hasn't really been tackled significantly, is great. But as long as you kind of look at it from an innovative standpoint, right? If you're trying to just take the same techniques you're trying to bring in from other competitions, it really just becomes another Formula One competition, right?
So you already expressed that you don't think Hyperloop will work kind of as proposed, full vacuum in these different technologies. What do you think a full scale Hyperloop looks like in your eyes?
I think personally, the biggest obstacle, in my opinion, is cost. And so I think if people are able to build a system that is efficient and cheap, that's sort of on the order of building even a highway or even like a high-speed rail, there's a lot of value to that. So I don't think it's the technology per se. I think it's more of how do you make it cheaper. So I think a future Hyperloop can definitely look like a vacuum type transport, but in terms of building a vacuum for hundreds of miles long, I feel like that's a bit too it's just not very scalable in my opinion. I think given the constraints we have with sort of the terrain and going above ground or underground, it really depends on sort of what is kind of allowable and what we are able to do in that time frame. So I think my vision would be it could be a combination of both a levitation system that uses both maglev and maybe some other it could be air levitation potentially, but maglev is probably a very common approach that people are taking because it already works. And I think what companies are doing right now with the suspension, with the linear motor for moving the pods is a very common approach too. So these two things, the linear motor plus maglev, are proven to work. And I think there's no issue with the technology itself. It's just the matter of building the actual track. I think the track itself is probably going to be the hardest obstacle.
So what are your thoughts on, so a while ago, the Boring Company made the Las Vegas tunnel, where essentially now you can just take a Tesla, put in, and autopilot will take you to the other end of the tunnel.
Mm-hmm.
What are your thoughts on that and what that could potentially mean in terms of, no longer having to worry about traffic on a normal road? Now it's streamlined underground. Where does that kind of fall into this?
So that's not really a hyperloop, right? It's more like an automated track system that is moving things in a much more efficient manner, which I think it solves a big problem, right? I mean, one of the biggest issues that we see right now is that being stuck in traffic, there's no order to how people are moving on the roads. And again, it's a safety hazard, right? If you imagine a very automated network that every car is sort of known to be at a certain precise location at any given second, you kind of can take out the sort of the anomaly or like the chance of having an accident, right? Because everything sort of has a time and place in which they're traveling, right? So there's a lot of value to that. I think in terms of if you can move cars at 100 to 150 miles an hour in that manner, that solves a huge problem in traffic, because no matter where you get on the track or where you get off, you're always going to be the same speed, right? Because the track is automated. And so right now, if you get on a highway, there's so many different variables involved in changing lanes, changing speeds, getting off the exit, getting on the exit, and all that adds delays to your actual time to destination, right? So ultimately, if looking at it from like an optimization problem, this whole automated track scheme is actually a great way to solve that problem.
So where do you think the system would be most successful? Like, what is the perfect case for this?
I would say so. I don't know about long distances, to be honest. I think if you're looking at like in a city to city travel, I don't think that's very useful for those kind of scenarios. But I think for intra-city travel, where you're within a city and you have to get from one part of the city to another part of the city, or maybe like, let's say you're going from the airport to the suburbs, right? Or there could be a lot of traffic, or maybe there's a traffic within the city around downtown or the suburbs. That could be a big way to kind of drive that, right? And I think there's a sort of an area where I think that kind of approach does work really well. And from a long distance perspective, right, I think the infrastructure has to be cheap enough to really make it worthwhile, unless that there's like a significant amount of super commuters that are going from like Dallas to Houston every month that really need the system that could be relevant to them, right? So I think that's really what I'm focused on.
Very cool. So you did an internship at P&G a while back. I'm wondering,
yeah.
Working on Tide Pods, I'm wondering what your thoughts are on the whole Tide Pod craze that happened recently.
You mean what just happened? I actually don't know what just happened on the Tide Pods. You mean what happened when?
I wouldn't say just happened, but
like a year or two ago? I think it was a year ago, yeah. When people were eating Tide Pods, did you see that?
So I thought that happened even in the beginning, because we were on the team that actually built the first version of the Tide Pods, and
That's so funny.
And this was like 8 years ago, and I think I remember this, and I think kids were just thinking it was like candy or something, and so we had to kind of put a lot of labels on the pods to make sure people aren't eating it, or at least tell the parents that it's like it's not for kids kind of thing. But the problem is that like we made this thing so look so delectable in a way. It's like you just want to eat it, but it's a really cool tech. I mean, it's like the way we I was working on the actual manufacturing lines that were building the pod, so we were doing a lot of work on so there's like 3 different sections. There's like the packaging, or like the chemical side that injects the detergent into the pockets, and there's like the machines that actually seal the pods, and there's like the packaging, and then the system that put everything into the boxes. And so from from my experience, I think Tide Pods is a really cool product that we worked on, and one of the most innovative things that I think that we got to build, right? Both from like the technology itself and like the way that it was being mass produced and being put into these buckets. And so nowadays you see a lot of companies, even like if you look at your typical dishwasher detergent, right? Even that's coming in pods, right? So I think it's a really cool product. I think maybe we could have done a better job of trying to communicate this is not for kids, but I think from like a product standpoint, it was something that I think was very, very unique and something that no one's really done before.
Yeah, I was amazed to see that. I feel like I've known you for quite a while now. I had no idea you were ever involved with Tide Pods or anything like that. Is that almost in a way like the ultimate compliment of like you made something that looks so good that people just got to eat it, you know?
Well, I think it really was cool how the team, the chemical engineering team was actually the coolest part. I think they're the ones that did the cool stuff where, being able to inject detergent or not detergent, the actual, the chemicals into the pockets and sealing them with the glue and not having that pop was really an amazing, like a technical feat, in my opinion. That was like the real innovation. Yeah.
So speaking about like innovation, just kind of doing things differently. I know that you were in the Plan 2 program here at UT, which I have a couple friends in, and I've always just kind of been really interested in just how different that program is. Do you think that, how do you think that kind of helped get you prepared for the careers that you've been able to do?
Yeah, so looking back now, I think Plan 2 was one of the programs I really enjoyed at UT. I was an electrical engineer and a Plan 2 major. And I really enjoyed Plan 2 because of it's sort of opened like my interest in like areas that are super non-engineering. And I think more of the creative arts, the philosophy, the writing, and all other things. I was doing some music classes as well. And, I think it just part of your brain just really for me, it's like, I think the creative part is really what drives a lot of the innovation. And I think, technically, I love engineering, but if I look back, I really think programs like Plan 2 were the ones that really kind of opened up your mind to like kind of new ideas and new ways of thinking. So I think looking back, I think it's really cool that you can do something like engineering plus something more arts focused, because I think that really helps you kind of think differently.
Yeah, and you have to do a lot of writing and engineering, right? So I'm sure that part really helped you.
Yeah, no, I think personally, I actually liked writing quite a bit, and I took some philosophy class in Plan 2, and I think it was very different from any other class I took, and I think I learned a lot of like logic and reasoning through that class, and I think that was something that was really valuable taking, looking back in time.
Yeah, that's awesome.
Mhm.
So you also, I think, did some program at NASA working on like simulated Mars rovers.
Oh, this was like
Was that
previous,
high
like
school?
I was about to say that's a
long time ago.
real far back
That's real. That's like
bottom of the
Yeah,
LinkedIn.
that's a real far
yeah,
back.
like 15 years ago, 10 years ago. I don't know.
Yeah.
This is more like a program that's like, we did at the Johnson Space Center.
Yeah.
So I grew up in Houston, right? So we had some programs there at the robotics clubs and stuff. And so we had these teams that we were working with at NASA to kind of thinking about like, what does it look like to kind of land a rover on Mars. It's more like a science experiment kind of thing. We weren't actually building any full-on rovers. It's like, more like a intern slash like a summer science camp kind of thing. And but that was actually my first foray into like more robotics and more engineering. And so that experience actually was what led me to do engineering in the first place at UT.
So
So
from like
with
a young
Perseverance
age,
landing yesterday, how does that kind of feel being part of super early on, kind of gain some experience with that, and then seeing something so technically complex as Perseverance landing?
Now you kind of put those two together. It's like, wow, I didn't realize that's yeah, it's really cool that yeah, I was watching the Mars landing yesterday, and it was really just the amount of effort that went into that and how simple it looked, right? It's like it worked real quickly, it generated the images, it got you the information that you needed. um I think there's so much that goes into like this kind of technology and automation. Like, everything was fully automated, fully autonomous, and I think looking at that and how far we've come in the past 10 years, like in terms of just reusable rockets, landing things autonomously. I think I'm so excited. That makes me just very excited about the future. I think we should really invest in like talent, and really invest in like training and understanding like what does it mean to build such systems, right? I mean, even if it's like a simulation or something that you're doing for a fun science project, long term wise, all those things that you learn really come back, right? I think even with Hyperloop, right? I never really had experience with Hyperloop or working on Hyperloop before, I came to engineering at UT. But like, it's just something that I just was very interested in. And given my past sort of a little bit of interest in like NASA and some of the work they did, that sparked a new, curiosity in me. And I think I would love to do more of this in the future. And I think right now, I know given the pandemic and all the different situations, it's hard to build stuff. And I'm more of a builder, right? I think, we, all of us here, we're all engineers. We love to build things. And I think my hope is that soon enough, we can get back to the labs and start building again.
Yeah, it was awesome to see. I think there were almost 2 million people watching that landing.
Yeah.
And people were sending in pictures of like their little kids watching, babies watching.
Mm-hmm.
And I think that's super important for inspiration, as you said. And your first experience with sort of engineering was that NASA program. And these kids that grow up will be these future builders of these Mars missions and these different things. So I think that's really cool. Yeah. And also just the landing system they use, the sky crane, is nuts to me.
Yeah.
They drop that thing and then it's just like, boop. And I think they gave it like a 90% chance of success. So they were super confident.
And I wonder how they're going to use a helicopter too. They have a little helicopter on board.
Yep.
Yeah.
Actually, and also one of my friends who was on the Hyperloop team at MIT, he actually built helped build the MOXIE thing, the thing that generates oxygen. So they're trying to see if that's going to do some cool stuff there on Mars. So I can say I know some Martians now who are now working on stuff that's already on Mars. So I think well, they're not physically on Mars, but I think eventually we can see some cool stuff out of this.
Yeah, and people also just don't realize how big that thing is. It's like almost the size of a Model X.
Yeah,
So
yeah.
It is massive.
Yeah.
And we just plopped it on Mars. It's crazy.
Yeah, I feel like there's still this idea that a lot of the general public has, like, oh yeah, like dog-sized, like just a little rover.
Yeah, for sure. Yeah, people don't realize.
Do you know how much it weighs? Is it like a half a ton?
I think
probably at least.
I think it's like a ton.
Oh wow, okay.
Yeah, it's crazy. So do we want to go back to the beginning of Texas Guadalupe? Sort of, you were talking earlier about the early days and you were just meeting in a room with a couple other people. Can you talk about why you started this and what the early experience was like?
Yeah, I think it was very, we were all just a bunch of grad students. We were just sort of like, we got basically, I remember getting an email from James. He's the one who started the team. And he was like, hey, we're looking for folks to take part in this new Hyperloop program that Elon Musk just released in this white paper. And I was like, I'm not really a mechanical, or like, I don't really have too much of experience in the space, but I do know some electronics, and maybe I can support from that angle. And so I just went to one of the meetings, and I ended up being the only EE there. So I ended up becoming the de facto EE lead. And then so we started looking at some initial systems, building some embedded systems for the autonomous navigation part and autonomous part of the Hyperloop pod. And we're just started really small, right? And I think it was like 7 or 8 of us in the classroom, and we were trying to hack stuff together with a bunch of Arduinos, and it wasn't even like a real embedded system. It was just like something that we just tried to put off the shelf together. And then later on, we had the whole design competition that happened at SpaceX, or not, it wasn't at SpaceX, it was actually at Texas A&M, which is in, College Station. So it turned out it wasn't too far away from us, and people from all over the world were coming to College Station. And it was like, we were just like a few hours away. So, James, myself, Deborah, Patrick, were like the 4 core people of the team. We just, took a trip out there with some folks in our team. And then we brought some models of our pod, and we were like playing around with air bearings, because air bearings seemed very interesting to us, and that was part of the original white paper. And this is before we even had an air bearing. We're like really just kind of infatuated with the idea of like floating on air. And we took that idea to space to the design review, and we were one of the few teams that actually had like an air bearing type of approach to the pod. And we actually weren't even selected for the first round of the competition. We were like, okay, well, we showed up a pretty cool prototype and we had some cool demos to show. But they picked like top 10 teams in that category. And we bet, we actually had some good conversations with some of the senior leaders at SpaceX who were there, and they were actually came by our booth and looked at our air bearing simulation, some of the work that we did on that end. And then we went back home and we're like, okay, well, we don't really have like any money to work with to kind of get into this competition, or we don't even have a slot into this competition. And we're like, okay, well, what are we going to do? And we didn't want to give up either. We just thought, okay, well, let's just kind of keep at it and keep building. And what happened was like 6 months later, we actually just ended up building a pod, like given like our own like networks. We started finding some initial companies that were willing to support us in our work at UT. And we called it the Guadalupe, and we just put a funny name to it, and then started raising some funds. And then we actually ended up finding an air bearing manufacturer, Airfloat, which ended up becoming one of our earliest sort of like supporters. And they didn't even know what they were getting themselves into. They're like, okay, well, these kids are trying to use our air bearings, and we're like, okay, we'll give them a shot. And they're not really in this whole high speed space because they use air bearings for moving heavy equipment. And so we're like, okay, well, just give us some of your sample air bearings, we'll kind of play around with them. And then like a few months later, we welded a whole frame, and we it was in like the aerospace building, I think at UT, I don't know which building it was, but we welded a whole frame in one of the basements, and we attached the air bearings to that. We and then put some air tanks on it, and then we did some just limited levitation tests, right? And then again, this is all before like the first real competition. And then we talked to SpaceX. We said, hey, we have this pod that we built. I know we didn't really get into the program, but we would love to still be involved in some way. And then they're like, they basically said, hey, based on our package, our design package, they said, okay, we can add you to our wait list. And so we were on the wait list for the first competition. And then after the first competition, we got into the second round. So they let us kind of come into the second round, but we were able to go see the first round of the competition at SpaceX. And that was really fun seeing what people actually developed in that program. And to be honest, we didn't see anyone that really built what we did. Like there was a few student teams that tried to do their own air bearings, but they weren't even that effective. And they were basically kind of running on wheels. And so we actually had a real air bearing type of solution. And so, we were kind of actually very, very energized by that, because we saw that no one else was really doing what we were doing. And I think we really just wanted to try this new innovation. And so we came back to the table and said, okay, well, we know we're in the second competition. Let's really make this happen. This is like August of 2017 when the actual thing was going to happen. And so we had another like 6 months to work this out. And we ended up building a full pod. We ended up building a whole track that you see at Pickle, the 150-foot track. I actually remember, going out there with a hammer and a machine. And I was a guy who was like helping to build the track. And we just laid the concrete on there. We had some support from local authorities to lay the concrete. We bought all the different aluminum sheets from a local, aluminum shop, laid it down on the floor. And then, it was just a lot of hard work in that heat. It was fully done in the summer, right? In the Texas summer, it was like 100+ degrees in the weather. And we were building this track out there. We're like literally like blood, sweat, and tears on that track. And so that's how Guadalupe started. And then we ended up, getting an innovation award that August for our work. So, yeah.
Wow. And then were you around when the two teams merged?
I believe I had graduated around that time, and I was still in Austin at the moment, but I do remember that we just decided to have all the Hyperloop development happen in one team, which I think makes sense looking back. It's like no reason to have multiple teams because that just divides too much of the work and labor. And so, we just thought the name would be Guadalupe because it's a cool name. So, I think people remember Guadalupe, and I think even at SpaceX, they're like, oh, who are these Guadalupe folks? I think it's a funny thing because we just love to have that little, uniqueness to us. And so it was fun to kind of, make sure that, we're all in the same team. We're all kind of in the same vision. And I think, seeing what you guys have done already in the past several years, just so much that there's still so much interest in the team. And so I think you guys really have something going for you guys. And I really hope that, just don't give up the steam, keep it up.
So going to MIT where kind of did you decide that you wanted to bring a new Hyperloop team to MIT, and what was that like, especially with Hyperloop one at MIT kind of being a done deal? There wasn't really anything to go off of there.
Yeah, it was actually really hard to start up a whole new team from scratch. We basically, when I joined MIT, there was no Hyperloop team anymore. It was just all defunct. Everyone had gone, graduated, completed. And actually, all the material that was built for Hyperloop 1 was just sort of either thrown out or donated or something. And so there was nothing really left of the material. And so that was one of the hardest challenges I've faced, to be honest, is to build a whole team from scratch. I mean, um, luckily I had some experience at Guadalupe that, I knew how the Hyperloop program worked. I knew the structure behind it. And so, but, we didn't have much time. We had like 6 months to design and to design, develop, and ultimately build a pod. And so ultimately I had to spend a lot of time on top of my research and classes to kind of build this team up. And we started from, we grew to about 30 people, both grad and undergrad students at MIT. Within a span of a few months, we started having weekly meetings, and people just started joining. I think people really wanted to see something happen. They wanted to see a new Hyperloop team flourish at MIT. So it was great to have that interest and that passion. And so that's really what drove everything. It's like people really were passionate about it. There were a lot of interest. And so we just kind of took that passion and just kind of spin it into something that was actually going to create something down the line. And so we also wanted to, personally, I wanted to kind of do more than what we did even in Guadalupe. In Guadalupe, we really demonstrated some initial technology with the air bearings. We weren't able to do some full-blown like higher speed testing of the air bearings and really try to see if we can take this to the next level. And so there's some unfinished business, in my opinion. And so part of me wanted to kind of at least take that next step. And so we sort of took the learnings we had from what I learned in Guadalupe, and we actually did some collaborations. You guys know with Patrick, who's one of my good friends, and we kind of looked at some new ideas, designs of building a fully autonomous pod that also had electric propulsion. I mean, in the first version that we did with Guadalupe, it was a simple pod that was going to be pushed by SpaceX. Right? There's no electric propulsion involved. Simple levitation, no like funny, like not funny, but no smart stuff that was really going on into the pod. In the MIT version, we were doing a lot of things like autonomous navigation, autonomous, things in the space of pneumatics, where we're doing everything all fully remote. Everything was electrically propelled. We were using, a 400-volt battery that we built from scratch. I mean, there were so many things, so many systems that we built on top of this initial design that made it, definitely more dangerous, but also, more exciting. And so I think it was a very tough problem because we were doing levitation, propulsion, navigation. There's so many different components that went into this. Braking, we had a different braking structure. We were initially thinking about two types of braking systems, both magnetic and both pneumatic. Friction brakes, but given the timeline of our competition, we just decided to have simple friction brakes because the purpose was to just generate to see how fast the air bearings could go. We weren't trying to we weren't trying to do everything at once, right? But we had to do electric propulsion because that was part of the competition requirements. And so we did all this in a span of 6 months, and then when we got into the competition, we had about 3 months to build. And then we actually had a battery fire like about a month before the competition, and we had to rebuild most of the pod from scratch. And so all that being done, we still ended up going to competition in August of 2019. This is 2 years after, the Guadalupe thing that we did. And we won another innovation award, and we actually won first in the US for passing all the tests. And so it was a crazy year. And I think I'm glossing over a lot of the details, but I think we did a lot more than that I had hoped that we could do. And I was really proud of the team for that effort.
That's awesome. I know we are kind of running out of time here within our hour time slot, but there's one last thing I'd like to talk about. And that's just kind of in general, your research, AR, VR, Magic Leap, kind of where do you think that technology is going? How do you think that can be improved, and what might it look like in our future?
Yeah, I think one of the biggest things that I've learned from I think my research, my area of interest of research is in optics and augmented reality. So I really think that AR is the future of the way we interact with digital content. So similar to how you have your 2D laptops or your screens, your desktops, there's one way to kind of interact with information. But when you're trying to do like 3D models, interacting with 3D imagery or engineering designs, being able to have a system like an AR VR headset to help you understand that engineering complexity, or even just understand content in general, from an educational perspective or from like a research perspective, there's so much you could do with that information. And so I believe that AR is a future of how we interact with data. And I in my time at Magic Leap, we were building some of the earliest wearable devices that used photonics. They're like a type of optics that are used for these kind of augmented reality systems. And we built some of the earliest photonics that went into these wearable devices. And now, you see a lot of companies building these really full-blown, high fidelity, high field of view systems that people are using for Oculus, for Magic Leap, for HoloLens. And a lot of this comes from really the research that we were doing at Magic Leap too. So there's a lot of potential, in my opinion, for the future of augmented reality. If you even look at the movies, or even like any space movie, you see people wearing helmets that have really cool heads-up displays and Iron Man type of visualization. And so I do think there's a lot of these things that tie together. I think what we're doing in augmented reality is going to be really impactful for what we're doing in space and what we're doing in transportation as well. So I do believe there's a lot of interesting things that are kind of coming together. But so that's like my other hobby, is to kind of work on some new AR VR projects. And at MIT, my research was in building some new AR VR prototypes and holographic displays that could maybe change the way we see and use information.
So it's always hardest to predict the future, but when do you think AR would be more integrated into our everyday lives?
I think we're still a little farther away. I think one of the biggest issues is the field of view, like how much field of view you're getting when you put on these headsets. Also, the battery power is still not optimized, and the amount of, I would say, sensors that are being integrated into this is really cool. It's almost like you're putting an autonomous vehicle on your forehead and seeing through that autonomous vehicle. It's still not at a point where I think everyone is going to be able to use it next year. Because it's very expensive too. Like one of these headsets could cost you, like an augmented reality wearable headset could cost you anywhere from like $1,000 to $2,000, right? It's like pretty expensive, more than a typical computer, right? And it doesn't do as much as a computer does, to be honest. And so until we get to that point, we won't be able to see it mainstream. But in research and education, I think there's a lot of value to that. And I think even at MIT, we created a whole immersion lab at one of our MIT nanotechnology buildings. We have a whole little department that's using AR, VR to do all kinds of cool visualizations on quantum computing, on photogrammetry, on things like understanding like chemistry or physical processes. So I think there's a lot of value to that for education. And ultimately, I think even for meetings, like I can imagine all of us being in our own holodeck one day and trying to kind of interact with each other and kind of, all as maybe holograms or real-time renderings. That all is a really big part of the next few years of research and development.
Yeah, being a mechanical engineer, and if I was able to do CAD in front of me and be like, oh, you know what, that socket wrench doesn't fit in there, I need to redesign that. That'd be just a game changer in and of itself.
Exactly. Yeah. And I can't wait for that. And I think, all these things that we talked about, like Tide Pods, like, or, NASA, or like, Hyperloop, or, engineering and, AR, VR, autonomous transportation, all these things kind of require innovation. I think what ultimately is going to happen is that like all these things are going to come together. It's like, the way you think about technology, the way you use technology, the way you, share and build is going to be really impacted by all these different things that we're working on. So I think, they may all seem different, but I think there's this underlying current of innovation that really is common amongst all of these things.
Well, with those wise words, I think we can sort of wrap it up. Thank you so much, Vik, for coming on. I really enjoyed this conversation, and I hope you did as well.
No, thank you guys. Thanks, Gavin. Thanks, David, for hosting.
Yeah, it's been an absolute blast.